So today we are working on Taylor and Maclaurin series, and they basically encompass what we will come to call a power series. Right? We've already done the convergence for a power series, and now we want to figure out how to create them. And as I've said, power series, and excuse the pun, are quite powerful in the term that they can be used in many different equations and ways to solve problems, one of which would be in differential equations. So our task today is to just kind of work with a sum here just to get the idea, then create both Taylor and Maclaurin series. I think I'm actually going to start with Maclaurin and then go back to Taylor. And then once we've developed the series, what can we start to do with them? So let's do this exercise at the beginning of the packet. So a power series representation for e to the x is this summation. X to the n over n factorial. So the problem here says, can you please tell us what e squared is? And then to prove that this summation is relevant, use 7 terms from the sum and approximate e squared. So e squared I have here, and check my calculation, is 7.38906. And that's just plugging in the calculator. The next part says, okay, excuse me, go ahead and take that summation and write out the first 7 terms. Well, to write out the first 7 terms, all we have to do is start plugging in n equals 0, then n equal 1, 2, and 3, and so on. So, if n is 0, we get x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial, and so on. Now it asks for the first 7, so if I start at 0, that means I got to go up to the power 6. And the only 2 there that I really care to simplify would be the first 2. Right, x to the 0 is 1, and 0 factorial by definition is also 1. So this term is 1. X to the first over 1 factorial is just x. So then plus the rest. The factorials you could do in your calculator. You don't need to write all those out if you don't want to. And in the case of the stuff we're going to do here in a little bit, it's probably best to leave them as factorials. So now it says approximate e squared using these terms. Well, this is a representation of e to the x. So how would we then approximate e squared? Well, we would just turn x into 2. So in all of these, let's plug in 2. Okay. And then if 2 is plugged into all of them, you get, as an approximation to e squared, (7.335 and a 6). not so bad. It's at least good to 1 decimal place. So one thing that I wanted to show you guys, right, we said we approximated e squared and we took 7 terms. And then down here we got 7.35, and up there we had 7.38. So as I said, it was good to 1 decimal place. Well, that value of x is pretty small, right? X equal 2 is not a big number. So what I've done here, let's see if this works. So I'm going to share my display with you. So it's going to go nuts here for a second. Do you guys see the Mathematica page? You can't see the graph? Okay. Wonder why that is. I think I'm probably making it worse right now. Problem is, it's when I'm in here, it's showing everything, and I can't just see the thing that I'm trying to fix. Did that help at all? Awesome. All right. Well, I had it work yesterday. Let me try one thing. I'll just delete this capture. And I will set up a new one. Okay, so the yellow curve here is e to the x. Notice it passes through 0, 1, and then gets close to the axis. The blue curve is our approximation to e to the x using only 7 terms. So notice that if x is beyond maybe 2.5, these two things start to separate, which means it's no longer going to be a good approximation. And on this end, so we can see for sure, they look like they're overlapping till about 2 or so, or a little after 2. And then you could start seeing some color of blue peeking out there, and then they're separating. So again, this approximation is really only good out to 2, if at anything. And notice that we did e squared, and it was only good to 1 decimal place. So if we zoomed in, it wouldn't be as accurate as we thought. All right, everybody back to the camera screen now with the board. Okay. So I just wanted to demonstrate the idea that these things are very powerful, but you have to understand the limitations. Right? There are certain values of x that they work well for. And if x is big, then you need a lot of terms to try to make a good approximation. All right, so let's learn how to build one of these power series representations. And we're going to start with the Maclaurin instead of the Taylor, because the Maclaurin's easier. And I believe we can transition into the Taylor pretty quickly. All right. So a Maclaurin series is a summation from n equals 0 to infinity. The nth derivative evaluated at 0 divided by n factorial times x to the n. So that is the Maclaurin. So what makes it a Maclaurin is that it's evaluated at 0. And if we were to write out the first couple terms, that's f of 0 plus, and that's the only thing, right? Because x to the 0 is 1, 0 factorial is 1. So, and then the 0th derivative just means the original function. Then we need f prime of 0 over 1 factorial times x to the first plus f double prime at 0 over 2 factorial x squared. And I'll write one more. It's f triple prime at 0 over 3 factorial times x cubed. So those are the first couple terms. Okay. Now the problem here says you're given f of x, which is equal to e to the minus 5x. Please use the first 20 terms to approximate e to the minus 15. So we want to know what's e to the minus 15, and we want to do a power series using the Maclaurin. So let's take a look at that. So what do we need? We've got factorials, we've got x's in here, but the most important thing we need are the derivatives, right? We've got the first, second, third, and so on, how many terms we want. So let's write out the first couple. So I've got f prime. So first derivative of this, we just bring down a minus 5. Second derivative, you bring down another minus 5. Third derivative, yet another one. And if we went to the fourth derivative, this would be, what, 625? Okay. So those are the derivatives, but the Maclaurin series requires us to plug in a equals 0. Or x equals 0, whatever you want to call it there. In this case, we call it a. All right, so f of 0, f prime, double prime, and there's that. So all these are exponentials, so they're really nice when we plug in 0, right? E to the minus 5 times 0, that's e to the 0 power. And we all know e to the 0 is just 1. So this one is 1. And then all of these just become their coefficients. Now yes, the problem does ask for the first 20 terms. I am not manually going to write out all 20, and I would not ask you to do that either. So let's write out the first couple terms of the series and see what it looks like. So the first term is just f of 0, so that's 1. The next term is f prime at 0, which is minus 5. Times x over 1 factorial. Next one is f double prime times x squared over 2 factorial. The following, f triple prime at 0 times x cubed over 3 factorial, and the last one we have written, 625, that would be x to the 4th over 4 factorial. So those are our first 5 terms of the Maclaurin series. Now we can easily get those from a computer program. That's how I found or created that chart a minute ago. But instead, what I would like you to do, because you're not going to be able to use a computer program, is use your calculator. So in your calculator, we need to express this sum so that we can plug it in. In order to do that, we then have to rewrite this sum, or the addition of these terms, as a summation. So we have to find a pattern. So what is the pattern here? Anybody notice anything? Right, it's alternating, good. Okay, so looks like some people are given some, what they're giving is their solutions. So, let's start with the denominator. This is technically divided by 0 factorial. Then we have 1, 2, 3, 4. So it looks like if we started at 0 and counted by 1, each denominator is that factorial, or n factorial. Then I notice that we've got 0 x's, x to the first, x to the second, x cubed, x to the 4th. So it looks like x is also to the power n, starting at 0. Then if I look at the coefficients, I've got 1 which is any number to the 0. 5. 5 squared. 5 cubed. 5 to the 4th. So 5 to the n. And then we've got to take care of that alternating term. So it's positive, negative, positive, negative. Alternating can always be done by -1 to a power. Because we're starting at 0, this can be -1 to the n. We can then put all 3 of these pieces together. And it would technically be to infinity. So let's do that, and then let's say an approximation is n equals 0. Now they wanted the first 20 terms. So technically that would be to 19. I'm just going to tell you guys, just go ahead and plug in 20. Make things easy on yourself. So then the top here could be -5x all to the n over n factorial. So in your calculator, you could plug in the sum from 0 to 20. Now instead of plugging in -5x, what are we going to be plugging in? Well, the problem originally asked for an approximation to e to the -15. So how do I make 5x look like 15? Well, I just make x 3, right? So in your calculator, you're going to be plugging in -15 inside the parentheses. And your n's will more than likely be x's in your calculator. That's okay. So can someone plug that in and tell me what they get? And would someone else go ahead and calculate e to the -15 and tell me what they get? Alright, so somebody got the number does seem a little off. Let me see if I have this written down. Alright, so let me just go ahead and do it real quick. Figure out what to do with my calculator. There we go. Alright, so first off, e to the -15 is 3.059. times 10 to the minus 7, I think it is. Okay. And if we do the sum, so we're going to go to math, option 10 or 0. X starts at 0 and runs to 20 or 19. Then we want to plug in negative 15 to the power x divided by, in parentheses, x, and go to math, probability, option 4 to get your factorial. I get 57,612 if I do to 20. And if I do to 19, you get negative 79,000. See, that was the one I had done before. So let's go ahead and run this to 19. And you get negative 79,065. Well, that's not even close, right? So the question is why? Can you all see the graph okay? All right, so this graph here is of the exponential, which is the yellow, and the blue, I think the yellow is the exponential. Yeah, the blue should be the approximation. So look, they look like they're okay out to maybe 3, negative 3. And recall this is e to the minus 5x. So x equaling negative 3. Actually, I guess we want to go to the other side. Let's do that. We want to go to 3, right? All right, so on this side, the exponential is riding the axis. But by the time we get to 3 for the approximation, the blue curve is nowhere near the axis. And I say nowhere near because look at this scale. Right, this number is negative 200,000 out here. So, if that's what we're trying to approximate, right? To get negative 15 up there, that's when x is 3. Well, look how far off we are. So that's telling us we need more terms in order to get a better fit. So what I did was I went back and I said, okay, and I did this one day. I said, how many terms do I need? I think it turned out to be somewhere around 50 some. So here I've shrunk down the curve quite a bit. And now I am a very good fit out at 3 with 53 terms. But look, it didn't get me very far, right? By 3.1, I'm already deviating. So I went from 20 terms to 54 terms. Just to get accurate to 3. So again, these kind of things are typically used for small angles, right? We talk about small angle approximations a lot. That's where these power series come in quite a bit. So if you take physics or engineering, right, you'll do, sine of theta for small angles is theta, and cosine of theta for small angles is 1. Well, those approximations come from a power series expansion. All right, so that was a Maclaurin series. Let's do another one. So I was asked many times yesterday, well, what would a test question look like for this stuff? My answer to that is I would give you a problem, which we'll see later, and I'll first say, okay, find a Maclaurin series for a part of the problem, then use said series to do the operation that I asked for, and also write the what's called the closed form of the series. And that comes from what we did over here. We rewrote the summation. All right, so the next Maclaurin series is given f of x is equal to sine of 2x. Use the first 20 terms to approximate sine of 10. So here's f prime, double prime, triple to the fourth. Let's see if that's enough. So derivative of sine is cosine, and I get a 2 out in front because of the chain rule. So 2 cosine 2x, and then derivative of cosine makes it minus the sine, and you get another 2 out in front. Again, derivative of sine is cosine, bring out another 2. We're actually going to need to go to the 5th derivative here at least. So sine, cosine, sine, cosine. This one's going to be positive sine, and then positive cosine. Guess I'm off the screen there a little bit. Let me shift it down. So the last term there is 32 cosine 2x. So now we need to find all of the functional values at 0. So now you might see why I went an extra term, because any one of these that has a sine function in it, when I plug in 0, it's going to go to 0. So the first, the second derivative, and the fourth derivative are all 0. Then any of them that are cosine of 0 is 1. So again, we would get the coefficients out of those. So the first derivative, we would get 2. Third derivative, we would get -8. And the fifth derivative, we would get 32. So then our job is to write out the first few terms. And I'll tell you now that a lot of people will say, oh, these are zeros, I don't have to include them. But they are quite important because you have to follow this pattern. So, sine of x is approximately equal to. I guess it would really be sine of 2x is what we're approximating. So, function at 0 is 0. First derivative is 2 times x over 1 factorial. The second derivative is 0 again, so the x squared term is going to disappear. Third derivative is -8 x cubed over 3 factorial. The fourth is 0 yet again, so the fourth, x to the fourth is going to disappear. And then finally, 32x to the fifth over 5 factorial. Can you guys see all of those okay? All right, great. Thank you. So again, and this is plus ... Can we come up with a pattern? So let's go ahead and just write out the ones that are still there. So that's 2x over 1 factorial minus 8x cubed over 3 factorial plus 32x to the fifth over 5 factorial. Again, what patterns do you see? It is alternating again. So yeah, you both are close. They are all odd. So the way we represent an odd number is 2n plus 1. So that's how we would represent the factorial there, where n starts at 0. So if n is 0, you get 1. If n is 1, you get 3. When n is 2, you get 5. So that works. We've also got to take care of the alternating. It starts at positive and then negative and then positive. So that's a -1 to the n. And then we've got x to the first, x cubed, x to the fifth. And guess what? I can write 8 as 2 cubed, and I can write 32 as 2 to the fifth. So in fact, we've got 2x to the first power, 2x to the third power, and 2x to the fifth power. So they are also two odd powers. So we've got 2x to the 2n plus 1. That is the closed form, right? The summation notation for that series. And if I were to show you the power series for sine of x, it looks exactly like this, but instead of 2x plugged in, it's just got an x here. So that's yet another pattern that we can start to recognize. So this problem said again to use the first 20 terms. So let's go to 19 and see what those numbers are. I think I may already have them. Let's see. I know sine of 10, at least to 3 decimal places, is 0.544 negative. Can you guys calculate that and that summation and tell me what you get? From what I recall, this is quite an accurate series. Can you start at n equal 1 and go to 20 instead, or does it have to start at n equals 0? So if you started at 1, you would be getting rid of that term. So yes, it would be quite different. Right, you'd be losing the biggest term that you possibly could get and truncating a term out here that's small. So for the summation, you got 0.544 0.21137, and let's just look. Oops. Let's look and see what sine of 10 is real quick. Remembering to be in radian mode. So sine of 10 is negative 0.544021109. So very close. Right, it's good out to like 8 decimal places. So that one is quite accurate. Alright, so we've done Maclaurin series. Now let's go ahead and do the Taylor series. And the difference with the Taylor series is that now, instead of evaluating at 0, we're going to evaluate at A. Am I okay to erase this, guys? Brentley, I remember that you had some trouble with the summation. Were you able to update your calculator? And if it's all right with you, would you mind just meeting me after class in a virtual meeting? And we can all go over it if you need. It's just a little hard to get the right lighting and things here with this setup. But I'll be happy to go over it with you if you don't mind doing that after class. Okay. Okay. So let me get rid of this. So, to make this a Taylor series now, then instead of 0, we're evaluating at A, and instead of x to the n, this is now x minus A to the n. So basically we're just shifting the Maclaurin series by A. And you can kind of think of this in a way like some trig functions. Recall that for trig functions you would shift, by pi, and inside you'd have sine of x minus pi or something like that. Alright, so let's try a Taylor series now. Same process, it's just when we plug in, we're plugging in A now instead of 0. So this first one's going to be simple. It's just going to ask us to do the Taylor series for e to the x. And about A equal 3. So f of x is e to the x. Let's find all its derivatives. Well, here's the nice thing. Because this is e to the x, we should know that its derivatives are all equal to the original, right? They're all just e to the x. And then if I plug a equal 3 in there, so f of a equals f prime equals f double prime, and so on, equals e of 3. So basically in this problem, everywhere we see f of a, f prime, whatever, f double prime, so on, we'll be plugging in e cubed. So this is e cubed plus e cubed x minus 3, because it's x minus a, over 1 factorial plus e cubed x minus 3 squared over 2 factorial plus e cubed x minus 3 cubed over 3 factorial, and so on. Now I stop with 3 or 4 terms because typically if I ask you to do a problem, I would say please give me the first 3 non-zero terms. So when I say non-zero, I mean calculate all of them and then cancel out the ones that are 0 and tell me the 3 that are left. Or you should have at least 3 left. So that's the Taylor series right there. That's done. That problem's real easy because it's e to the x. If we wanted, we could rewrite this one. And it would look something like this. Right, everything there has an e cubed in it. So I just pulled that out in front. And then this right here, right, it's got x minus 3 to the 0, 1, 2, and 3. So that's x minus 3 to the n. And on the bottom we've got 0 factorial, 1, 2, 3, so on. So n factorial. So that is the closed form for that Taylor series. Again, you will notice that this right here looks a lot like e to the x, except now it's x minus 3. And because of that, that's why we get this term out front. So that is the most basic Taylor series that we can do. If it's all right with you, I will go ahead and do the next one. Actually, I'll give you guys a second to jot that down if you like. What do we plug in for x? Well, and this time it didn't ask us to do an approximation anything. It just asked for us to create a Taylor series. So we are not plugging in at all in this problem. All right. So last Taylor series that we're going to create using this form is for cosine of x. And this is at a equal pi. So let's find the derivatives. Derivatives of cosine is minus the sine. And derivative of sine is cosine. Have to keep the negative out in front. Derivative of cosine again gives us another negative and a sine. So it becomes positive. And then finally, another derivative will get us back to cosine. Now I could have kept going, but because I'm plugging in pi, the sine functions are going to go away, and the cosines are going to stay. So cosine of pi is -1. Any of them that are sine go to 0. Cosine pi is -1 with another negative out front, so +1. And then finally, cosine of pi is -1. Again, let's write out all of the terms and then simplify. So I need the function evaluated at a. Well, that's -1 plus the first derivative, that's 0, times x minus a over 1 factorial. Second derivative is 1 times x minus a squared over 2 factorial. Third derivative gives me 0. And then finally, the fourth derivative is a -1. So, what's left over? Well, this term goes to 0. So does this one. So I'm left with -1 plus x minus a. So instead of a, I should be plugging in pi. So x minus pi squared. Okay. So x minus pi squared over 2 factorial minus x minus pi to the 4th over 4 factorial. And again, that continues. So those are my first 3 terms. If I wanted to write that in closed form, I've got an x minus pi everywhere to some power. I've got some kind of factorial. I've also got an alternating portion. However, it starts at negative this time. So I need a -1 to something. I have an x minus pi to something and a something factorial. Notice the powers are all even. They're 0, 2, and 4. An even number is represented by 2n. So x minus pi to the 2n will give you 0, x minus pi squared, and x minus pi to the 4th. Sorry, I should have said 1 here. It's x minus pi to the 0, which is 1. The bottom is also 0 factorial, 2 factorial, 4 factorial, so it is 2n factorial. Now if n starts at 0, these two work out just fine, which means I need to make this to the n plus 1. Because if I plug 0 in here, right, -1 to the 0 would give me a positive. So it can't just be n. If I make it n plus 1, then it'll start as a negative. You could also do n minus 1, that's an option. Any questions about how to create a Taylor series or how to get the closed form? Anybody hate or love these so far? All right, so I would like to go ahead and do a few applications. Yeah, the closed form is difficult, right? You really got to figure out the pattern. But once you see enough of them, it starts to come to you. So the last part of this packet says representing functions as power series. So first I wanted to point out okay, so given common power series, can you write other functions as a power series? Well, of course we can. And then the question is, but why? Why is that important to us? Well, there are problems in integration that I could give you that either you do not know how to solve or are quite strenuous. And you could simply use an approximation and integrate that, and it'll come out just as good. So let's look at a few of these. It says, represent each function as a power series using the table of power series. So I'm given f of x equals x cubed cosh of x. Now, power series are already polynomials. So something like x cubed is fine. We want to replace this function that you've probably never heard of, right? So that is the hyperbolic cosine. Don't freak out. It's probably the only time you're going to see it in this class. You may see it in Calc 3 or other classes that you take. This guy has a common power series. And again, this one's not on that sheet only because this is the only time I'm going to do it. But this really drives home the point, because here's a function you've never seen before, and yet we can represent it as something that you can easily handle. So that's the power series for the hyperbolic cosine, or cosh. If I want to know, or if I want a representation for this function, Well, then I simply replace the cosh function with this summation. So this is x cubed times the sum n equals 0 to infinity, x to the 2n over 2n factorial. This x cubed out here has no n's in it, so it can go in and out of the summation freely. I'm going to go ahead and take it inside and multiply it by that x to the 2n. Recall that when we multiply same base with exponents, we add the exponents. So this results in a new sum, n equals 0 to infinity, x to the 2n plus 3 over 2n factorial. That is the power series representation for the function x cubed cosh of x. So if for some reason I decided to ask you to integrate that function and you obviously have no idea what it is, you could use this. You could write out the first few terms of this power series. Because it is a polynomial, right, you'll get things like x to the 5th and x to the 7th. And those are really, really easy to work with and really easy to integrate. So let's try a few more. The second one here says f of x is equal to x over 1 plus x. This one might be a little difficult to decide what we're plugging in for when first looking at it. We're going to leave this x alone up top because multiplying by an x is not something hard to do when you were dealing with polynomials. The 1 over 1 plus x does have a power series representation. So 1 over 1 plus x is equal to the summation from n equals 0 to infinity, negative 1 to the n, x to the n. So again, f of x is now equal to x times the summation. And again, this x outside can easily go inside. By making this x to the n plus 1. So I'm sure this task sort of seems mundane to you. But let me go ahead and finish up this last one, and I'll do one example of what this is used for. So we can kind of put it all together. The last one here says we've got the function f of x equal to cosine x over x squared. In this case, it is okay to have 1 over x squared. Right? We can divide by a polynomial. We want to represent cosine as a power series. And you can find this one on that chart that I just put up for you. It's negative 1 to the n, x to the 2n over 2n factorial. So again, f of x is equal to 1 over x squared times the sum okay. And if I want to take this x squared in here, then I would just subtract it from that exponent. So that then would be the power series representation of cosine of x over x squared. So any questions about that before I do a problem of the next packet? Right. So I would like you guys for this next packet to take a look at the first problem and try that on your own, or the applications of series. When I say try that on your own, I mean after class or sometime tomorrow if you have time. I am going to go ahead and do the first problem on the second page, which is approximating a definite integral. So I have an integral here. It is the integral from 0 to 0.4, 1 over 1 plus x to the 4th dx. That's not necessarily a fun integral to do. We could do a trig substitution and solve this. Instead, let's use the fact that 1 over 1 plus x is equal to a summation from n equals 0 to infinity of -1 to the n, x to the n. So this looks a lot like this function. The only difference is that instead of x, I have x to the 4th. So if instead I plug in x to the 4th here, well then this here becomes x to the 4th to the n. Or x to the 4n. Knowing that, I can write out the first few terms. And here it asks us to use the first 6. So when n is 0, we get a positive term, and x to the 0 is 1. When n is 1, -1 to the 1 power is negative. Then we get x to the 4 times 1, or x to the 4th. When n is 2, we're going to get a positive, because -1 squared is positive. X to the 4 times 2 is x to the 8th. And I'll just jot down the rest. You should hopefully see the pattern. Right, it's given to you by the summation. That is the first 6 terms of that power series. All right. So if this is the representation of that function, well then I can just integrate that. So integrate 0 to 0.4 of 1 minus x to the 4th plus x to the 8th minus x to the 12th and so on dx. And we should all love this guy because the integral is simple for polynomials. I see there's a little bit of a glare there. There you go. Must be coming back off the computer screen. So, if I integrate this, then I get, as an approximation, x minus x to the 5th over 5 plus x to the 9th over 9 and so on. And this is all evaluated from 0 to 0.4. So really I just got to plug 0.4 into all of those, and I'll spare you the calculation. So this is 0.397951. And if you were to plug this original integral into your calculator and do the FNINT, you get 0.397981. So not so bad, especially considering the amount of trouble we had to go through to calculate that with polynomials is very minuscule compared to if we tried to do it by hand using the trig substitution. So that's the last example I'm going to do for you today. We're going to finish up this packet next time. I'm going to go ahead and stop recording.